Hey, what's up guys? Hope you are doing well. I'm Arvind from Precision Data Science. Today we're going to be working on California house price prediction dataset. In this dataset, we have housing information based on California census data, and we're going to be building a machine learning model to predict the median house prices. So buckle up, and without further ado, let's dive into the video. First, we are going to import necessary libraries such as NumPy and Pandas to work on the array data and data frame. Next, we will import Matplotlib and Seaborn for data visualization, and then ignore the warnings to have a cleaner output. We will read the CSV file using read_CSV method and assign it to a data frame df. We will display the first few rows and the last few rows using head and tail method. Here we can see the columns data, which includes metrics such as longitude, latitude, population, median income, median housing price, etc. for each block in California. Generally, a block group is the smallest geographical unit for which the US Census Bureau publishes sample data, and a block group typically has a population of around 600 to 3000 people. Next, df.shape method shows the number of rows and columns. Here we have 20,640 rows representing each block and 10 columns representing each parameter. df.info method provides a summary of data frame, which includes missing values and data type for each column. Here we have 20,640 entries, and all except the total bedroom column are non-null values, which means that there is no missing data for these columns except the bedroom column. Next, df.isNull.sum method shows the number of missing data for each column, and here we can see that we have 207 missing values for the total bedroom column. We'll quickly check the median value for the bedroom column, and the median value turns out to be 435. We're gonna replace the missing values in the total bedroom column with the median value using fill_na method, and then we're gonna run the isNull.sum method to see if there are any missing values. As we can see, we don't have any missing data in the dataset now. Describe method applied to the median house value column shows the distribution of data for house median value. We can see that the maximum value is around 500,000 and the minimum value is around 15,000. With df.nUnique method, we can see the number of unique values in each column, and generally columns with categorical values will have less unique values. Running the value counts method for the ocean proximity column shows the distribution of values for each category, and we can see that the island category has only 5 blocks while others have block data of around thousands. In order for the machine learning model to work, we need to convert the categorical values into numerical values. For that, we'll be using one-hot encoding technique to assign each category to a separate column. Pandas has a simple method called getDummies, which applies one-hot encoding technique to the categorical columns. We're going to apply the method and check the columns after one-hot encoding. With df.columns method, we can see that the ocean proximity column has been replaced by 5 columns representing the presence of each category. We're going to see the top 5 rows with the head method, and we can see that the ocean proximity column has been replaced by 5 columns with Boolean values, that is true or false. Since we are planning to predict the median house values, we're going to run the correlation method on the target column, that is median house value columns, to see the correlation between the target and the other columns. Here we see negatively correlated features like longitude, latitude, population, etc. And we have positively correlated features like median income, total rooms, total bedroom, etc. Next, we need to handle the outliers. For that, we're going to compute Q1 and Q3, which represents the value of first and third quantiles. We will compute the IQR, the interquartile range, which is nothing but the difference between Q3 and Q1. We're going to compute the upper and lower limit, which is given by these formulas, and anything outside of these upper and lower limit are considered as outliers and need to be clipped within this range. This range can be easily represented using box plot, and we'll try to compare the data before and after clipping. The figure on the left shows the box plot before clipping, and the figure on the right shows the box plot after clipping. We'll run the process for median house values and see the vanishing of the outliers visually. Next, we'll assign the group of columns requiring outlier treatment to a variable myColumns and run a for loop to treat the outliers in each group. For some columns, we can see that there are no outliers and hence there is no change, while for others the outliers have been clipped. Next, we are going to create 3 more additional columns, that is room per total bedrooms, and next median income per population, and then total rooms per household. So these extra features are going to help the machine learning model in making better prediction. Now, in order to make predictions, we have to separate the features and the target. For feature, we are considering all the columns except the target column. that is the median house value column, and for target column we are considering only the median house value column. For training the machine learning model, we need to split the data into training and testing set, and for that we'll import the train test split from the scikit-learn library. We will consider 20% for the test set and 80% for the training set with our random state of 1687. Next, we'll scale the data to standardize the feature values, and for that we'll import standard scaler from the scikit-learn library. We'll instantiate the standard scaler and fit transform for the training data and transform for the testing data. Now let's shift gears to the machine learning model implementation. Here we are using XGBoost Regressor, which uses gradient boosting method, that is combining weak learners with a learning rate and regularization technique to evolve them to make a strong machine learning model. We'll instantiate the model with same random state of 1687 and fit the model for the training data. After the model learns by fitting the data, we're going to predict the label values for the test set. For evaluation, we're going to import certain metrics such as mean square error and R2 score. Mean square error is the measure of square of the prediction errors, and R2 score is the regression score function, which shows how well the model predicts the outcome and typically varies from 0 being the worst to 1 being the best. We'll import the mean square error and R2 score from the scikit-learn library and try to find the values by comparing the predicted and test values. Here we are getting an R2 score of 0.8, which is good, and RMSE of around 47,000, which is again a decent value. To verify the results, we'll do a cross-validation across the dataset using cross-val score from the scikit-learn library. We'll apply the cross-validation across the training set with scoring as mean square error and a CV value of 4, so which represents the 4-fold cross-validation. After displaying the scores, we can see that the mean RMSE is almost same as the test predicted values, and we have a good RMSE and R2 score of around 47,000 and 0.8 respectively. Now, in order to make improvements to the machine learning model, we'll try to optimize the parameters within the XGBoost model. For that, we'll be using gridsearchCV method to make the optimization. We'll import the gridsearchCV method from the scikit-learn library and create a search space for all the parameters to be searched. Here we are considering n estimators, maximum depth, and learning rate as the parameters. We will instantiate the gridsearchCV with estimator as XGBoost, parameter grid for searching as search space, scoring as negative RMSE, and a cross-validation of 4. We will fit the gridsearchCV for the training set and let it search the best parameter with the best score. In the end, we'll print the best score and the best parameters. Okay, after printing the best score, we have an RMSE of around 45,000. We will quickly run the model with the best parameters and see the improved RMSE for the test set. As we can see, we have an improved RMSE score of around 45,000 and R2 score of 0.81. If you want further improvement, you guys can try with more parameters in the grid search and let me know your best score in the comments. So that's all I have today, guys. If you enjoyed this video so far, please like the video, subscribe and hit the bell icon to see more content. Thank you.